on Thursday, we now need to carry on with double integrals. There is no register today, which is fortunate for the three quarters of the class isn't here. Thank you for coming, everybody. So I did one example on double integrals on Thursday. It was pretty much one of the easiest possible examples. The thing that made it so easy was the fact that the limits of integration were just numbers. The region of integration was a rectangle. I'm now going to do exercise 2, where the region is not a rectangle. We need to integrate this thing, x plus y dA, where R is the region in R2 bounded by these two graphs. Let's have a look. There's y equals 2x squared, and then there's y equals 1 plus x squared, and it looks like that. Okay, and you can solve for those intersection points, and they're -1 and 1, and that over there would be a 2, and this is my region R. Catch up with me, stylus. There we go. Alright, that's my region R there. Now, on Thursday, I did the one example in class, and then in second period, quite a lot of you were very intrepid and continued on with doing exercise 2. But a major mistake that everybody was making, and unsurprisingly, because this is only the second double integral you've ever seen, but here is what's wrong. Okay? To describe R as, let's have a look, let's do dy dx, y going from 0 to 2, and x going from -1 to 1. Okay, that is wrong, okay? Because what that is describing is a rectangle that goes from -1 to 1 and from 0 to 2. That's what that is describing. It's saying we want all the points where x is between -1 and 1 and y is between 0 and 2. And that, of course, is not our region. Our region is actually that curvy shape rather than that rectangle. Okay? So what we're going to do is our limits of integration are not going to be just numbers. As soon as your limits of integration are just numbers, what you're describing is a rectangle. So people were calling me over and they were saying, have I done this right? And without even looking to see what numbers were there, the fact that there were 4 numbers there was enough for me to say, no, that's incorrect, because I can see that it's a rectangle. Very common mistake to make, but a mistake nonetheless. So what we're going to do is we're actually going to have limits of integration that are not numbers. All right? The limits of integration, or at least the inside integral, the first one that we do, is going to have variables in the limits of integration. So this is what is correct. Integral, x plus y. I'm going to do y first and then x. Okay? Now let me go look at the picture there. Now y is interested in the vertical extent of my region, and x is interested in the horizontal extent of my region. So y we always read from bottom to top, and the bottom of my region is 2x squared. And the top of my region is 1 plus x squared. Okay, 1 plus x squared. For values of x that go from -1 to 1. Now notice how I said that. I'm going to repeat it again. Y goes from, or extends from, y goes from 2x squared to 1 plus x squared for values of x that extend from -1 to 1. So I don't need to put variables into my x integral, because the curviness, if you will, of the region has already been built into the y integral, and all I need to now say is what values of x are applicable. I could have done the x integral first, but it would have been a lot more difficult. If I'd done the x, well, not difficult, just awkward. It would have been more awkward. If I did the x integral first, then I mean, the integrand itself doesn't care which one goes first, x or y, because it's the integrand, just x plus y, nice and symmetric. But the region really does care, because if I do x first, x is interested in the horizontal extent of the region. So you read from left to right. So you have to say, okay, what's the left edge of my region and what's the right edge of my region? And the answer to that question is going to be different depending on where you look in your region. If x integral first, what I'm going to do is I'm going to chop up my picture into 3 regions. There's the one parabola, there's the other. I'm going to chop it up into 3 regions. You know what? I'm just going to draw this top parabola a little bit more curvy so that I have some space. Something like that. Okay. That region there, and this region here, I would have to treat in 3 separate double integrals. I would have to say, so I'm just going to do, I would have to say the double integral from, let's have a look. I'm going to have to make x the subject of those parabolas. So let's have a look. If y equals 2x squared, then x squared is y over 2. So this is x equals minus square root of y over 2, and this is x equals positive square root of y over 2. Okay, and then that other parabola, it's y equals 1 plus x squared, so x squared is y minus 1. So this is x equals the minus square root of y minus 1, and this over here is x equals the positive square root of y minus 1. Okay, cool. So the first double integral, I'm going to do that little squiggly region on the top left. X will go from the left edge to the right edge for values of y that go from 1 to 2, plus, now I'm going to do the little squiggly region on the top right. X goes from the left edge to, I got that other one wrong, didn't I? But I'll come back and correct it. Goes from the left edge to the right edge for values of y that go from 1 to 2. Plus, okay, I'm just going to go back and correct it. Mostly it's because my picture is so scrunched that I'm reading the wrong things off the picture. It's actually the other way around. The left edge is actually the steeper parabola, so it's minus square root y minus y over 2. And the right edge is that flatter parabola, minus square root y minus 1. Sorry about that, I got them the wrong way around. And then I'll do the big squiggly bit at the bottom. So it's plus double integral, double integral. Left edge is the minus side of that one parabola to the plus side of that same parabola for y values to go from 0 to 1. Now there's nothing wrong with all that stuff that I've written on the right there. You can totally do it. It's completely correct. But it's a lot more awkward than that thing on the left side of the page. The thing on the left side of the page is just a single double integral. Question at the back. So I think I'm going to need a bigger picture. So let me actually draw my picture bigger. Catch up with, with me, stylus. Here we go. Nope. There we go. And there. Okay. So in this region over here, if I'm just looking at that little piece, my left edge of my region is y equals, not y, I beg your pardon, x equals minus square root y over 2, and the right edge is x equals minus square root of y minus 1, and of course I got those from making x the subject of the two parabola equations, where the minus square root is the left half and the plus square root is the right half. Okay, so when you're creating, if you're insisting that x be the variable that's integrated first, You've got to read your region from left to right, not top to bottom or bottom to top or whatever. You're not interested in the vertical extent, you're interested in the horizontal extent. So you read from left to right. What curve describes the right edge of my region? What curve describes, left first and then right. Getting confused between my left and right here. Quite a lot of people are playing on their phones. Your phone is not going to write your exam for you. Not this year. The rate at which phones are improving. One of these days, the robots are going to take over the world. We're going to be left ignorant because we're going to have put too much intelligence in the hands of our gadgets. There you go. There's a dystopian view for you. Okay, and then we have to treat that second region over there in a completely separate integral because the left and the right are different. When we ask ourselves what's the left edge and what's the right edge of our region, we're going to come up with a different answer than what we did with that first region. So y equals x. Come on, Tracy. X. It's not that hard. X equals, what's that one? That's the square root of y minus 1, and that's the square root of y over 2. And those will be the left and right in my second region. And then in this third region, the left edge is this thing. X, why again? Good grief. Shows our habits are ingrained. One's so used to writing y equals that you don't even think about it. Square root of y over 2. And the right edge is x equals square root y over 2. Okay. Question. Could you please keep quiet so I can hear the gentleman at the back? Thank you. So you always, in your region, you can think of it in terms of, let me use the third color here, you can think of it in terms of drawing a horizontal strip across your region. Horizontal because x is going first. And then asking yourself, where is the left edge of that strip and where is the right edge of that strip? And that would be the beginning and the end. But then you can see, if we take that long strip that's at the bottom, sorry, it's a bit squiff, it's supposed to be horizontal. If we start with that strip right down at the bottom, and then we make it get higher and higher, the left and the right edges are going to move further apart from one another, but they'll still be described by the same curves. The left and the right edges will still be on that lower down parabola. But as soon as we get as high as y equals 1, we can no longer draw our strip as one solid strip. We have to divide it, we have to have two little ones. And that's why that bottom region is different from those two top regions. So this is why we have to divide it into 3. So, bottom line here is, if you have a region and you have a choice about order of integration, pause and think about which one goes first, because it could make a very big difference to your limits of integration. Okay, I'm going to solve this problem using y first. So my integral, which I'm just going to call I, is integral x plus y dy dx, where y goes from 2x squared, in other words y equals 2x squared, to y equals 1 plus x squared, for values of x that go from minus 1 to 1. Okay. So we say, what did I differentiate with respect to y to get x plus y? And the answer will be xy plus a half y squared. And then we plug those limits of integration into y. It'll be x plus x cubed, plus it'll be a half that squared. So it'll be a half. I'm hearing lots of muttering. Have I made a mistake? No. Okay. I do make mistakes. You know that. So do correct me if you see anything. That's squared. So that'll be 2x squared. So it'll just be x squared. Yeah, and then that'll be x to the 4, so it'll be a half x to the 4. Minus 2 times 2x squared, so it's x times 2x squared, so it's 2x cubed. Minus, that'll be 4x to the 4, so it'll be 2x to the 4. Okay, if I haven't been silly, that's what I get in the next line. Catch up with me, stylus, please. There we go. And then that's a polynomial, and then you just integrate that polynomial, and hopefully you can integrate polynomials by the time you get to second year. Can you? Of course you can. It's a polynomial. If somebody had just spent 5 minutes telling you what an integral was in high school, you could have done that. And the answer is 16 over 15. With a little bit of fraction work. Okay, you give it a go. You try numbers 3 and 4. They're actually both very easy. They're both kind of like exercise 1. Neither of them is like exercise 2. Okay, so double integrals, I hope after you've done a few, you will conclude that they're not very hard. You only ever integrate with respect to one variable at a time, so all integration in a sense is single variable integration, the actual algebra of it, the actual doing of the integral. The hardest part in all of these integrals throughout this course is setting it up. That's always the hardest part. And in double integrals, that's usually not too tricky. It's a nice two-dimensional region that you're describing. It's not a piece of surface. It's not a three-dimensional region. You can draw it quite easily, and you can usually describe the limits of integration without too much stress. After you've done a few, just for practice, start to get the hang of it. It's not too hard. If you get a double integral in a test or an exam, then you should think, hooray, because that's going to be marks in your pocket. And pretty much the only way that a double integral can be made slightly tricky is by giving it to you with the order of integration already defined, and yet you can't actually do it that way, and you're forced to change the order of integration. So let's do that. Waiting for my stylus to catch up with me. It's having a bit of a snooze. Changing the order of integration. And the best way to demonstrate that is simply with an example. Should I actually just do a sentence for the sake of the notes? Occasionally, a double integral is presented with a particular order of integration built in, in other words, not just dA, but actually dx, dy, or dy, dx actually already there. What is that noise that I'm hearing? Is it coming from outside the lecture theatre? Is it somebody's phone being incredibly noisy? No. Am I the only one hearing it? Am I going mad? That's also a possibility. Okay, yes, somebody said. Occasionally a double integral is presented with a particular order of integration built in. We can change the order of integration. We can always change the order of integration. And basically the system is the given limits allow us to draw a diagram, and the diagram allows us to change the order. And I will demonstrate with exercise 6. It says evaluate. Let's have a look at sine y squared dy dx. Okay, so if you look at that, it says, okay, you got to ask yourself, what did I differentiate with respect to y to get sine y squared? And you're not going to be able to answer that question. It's not cos y squared, because cos y squared would give us a sine y squared, sure, but it would also give us a times by 2y. So it's not okay, let me actually, that's just going to be too confusing with all the symbols. let me say, so d by dy of cos y squared is sine y squared, which we do want, but it's times by 2y, which we don't want. But then you might say, okay, cool, well then instead of having cos y squared on the left there, why not have cos y squared over 2y? Because then the 2y will cancel. But that also won't do. Because then we have to do quotient rule on that thing. Or you could think of it as product rule. If you think of the 2y as being like a times by 2y to the minus 1. But what will we get? We'll get 4y squared at the bottom. We'll get, differentiate the numerator. Times by denominator. Minus, leave the numerator, and times by the derivative. So what will that be? That will be sine y squared, sure enough, but it'll be minus cos y squared over 2y squared. So by dividing by 2y, we have got one term that looks like what we want it to look like, but now we've gained this other term with some quite heavy baggage that we don't want at all. Bottom line is, we can't actually integrate sine y squared with respect to y. So we need to change the order of integration. So what we're going to do is we're going to draw the picture that's described by these limits. That says y equals x and y equals 1. Okay, the integral is going from y equals x to y equals 1. So I'm going to draw y equals x. I'm going to draw y equals 1. Now be careful. Sometimes when one draws one's curves, you end up, if you just look at your picture, you end up with multiple potential regions in your picture. In order to tell which region it is that you really want, you've also got to think not just of the actual individual curves y equals x and y equals 1, but the y goes from y equals x. So y equals x is the bottom to y equals 1. Y equals 1 is the top. Okay, the noise is getting louder. Am I getting madder? This is my region over here. Okay? Our region goes from y equals x to y equals 1. So y equals x is the bottom of my region. Y equals 1 is the top of my region for values of x that go from x equals 0 to x equals 1. It's your inside integral that gives the sort of shape of your region, that says whether your edges are curves or what they are. Your outside integral just kind of gives you the beginning value and the end value of the last variable to go. So your last integral sign always just has numbers in it. But your inside one has the sort of instructions that give you your shape. So I'm going to call this integral I, as is my want. Stylus, you're having a very snoozy day today. So my integral, I can instead, the integrand doesn't change. The integrand doesn't change at all, but I'm going to change my order. X is going to go first. So X is going to go from left to right. X is going to go from x equals 0, the y-axis, to x equals y, that oblique line, for values of y that go from 0 to 1. Do not simply swap these. Okay? Very common error. It's a very distressing error because it indicates no understanding, but unfortunately, or very little understanding. But it is unfortunately and distressingly and dismayingly a common error for people to think, okay, I need to change the order of integration. That simply means I need to swap my integral signs. That's not going to help at all. It's not going to help in a variety of different ways. One way is you're still going to end up with variables in your answer. And another is you're not going to be able to avoid the sort of impossible integral that you were trying to avoid. Anyway, I hope it's clear that that's not good enough. So you go from the integral that you can't solve You take those limits, you draw a picture, and then you use the picture to then construct your new limits. Okay, and now it becomes easy. We ask ourselves, what did I differentiate with respect to x to get sine y squared? As far as x is concerned, sine y squared is just a funny looking constant. Yes, question in the front. Because I've been given, let me rewrite this because it's a bit stretched out. Let me squash it in a bit more. The given integral has a y equals x in it. So if you look at the actual question, it says the integral goes from x to 1, and that x is y equals x, and the 1 is y equals 1. Did I answer your question? Okay, cool. Equals, okay, and then those get substituted into the x, so that's y sine y squared, ty. Now I can integrate that, because now that I have the y sitting in front of the sine, chain rule is taken care of. So I ask myself, what did I differentiate with respect to y to get y sine y squared? And the answer is 1/2 cos y squared. So that will be 1/2 cos 1 minus 1/2 cos 0. Cos of 0 is 1, so that's just 1/2 cos 1 minus 1. You give it a go. Try number 7. Questions about this one? Is it supposed to be a negative? Which line? The cos y squared? Half cos 1 minus 1/2 cos y squared. I'm being blind. Yeah? No, because yes it is. Because yes, quite right. I made a sign mistake throughout. Thank you very much. Sure. Shouldn't have taken me that long to notice that. Well, in fact, I didn't notice that. Shouldn't have taken me that long to know what you were talking about. Okay, but you try number 7 and you make fewer mistakes than me. How about that? Catch up with me, stylist. There we go. I'll give you the answer so you can check yourself.